Today we have the final EAKTS for the year, and we're very happy to have Joseph Ayoub, who will tell us something about rigid analytic motivic sheaves.
Yeah, thank you very much for the invitation. It's actually my first Zoom talk so far. But I hope I have some experience already because I've been teaching on this tablet since 2 months now, and yeah, so I hope it will go fine. So I want to report on some recent work with Martin Gallauer and Alberto Vezzani on rigid analytic motivic sheaves. And so somehow the goal of this project was somehow to understand for example the functoriality of the construction that takes a rigid analytic space and give us the category of rigid analytic motives or motivic sheaves on S. So this is, and so we do consider this as an infinity category. And so this is supposed to be the analog of the Morel-Voivodski stable homotopy category over a scheme. So except that here S is not a scheme, it would be an analytic space. So we wanted somehow to understand the functoriality of this assignment. And for instance, trying to develop as much as we can the 6 functor formalism in this situation. But somehow, I will mention this later in my talk. Give you precise statement. But somehow I would like to maybe speak or stress more about one particular result which I find maybe more interesting. Which is about the following question. So, how to understand, or if you prefer, maybe reconstruct this category rig, SH of S, using infinity categories of usual motives. And this question somehow is, I think, is answered in quite nice way in this work. And so I want to start by giving you an example of what do I mean by this. So this was an old result of mine where somehow that gives indeed a way to think about rigid analytic motives in a purely algebraic way. So I will give an answer to this question, or I'll describe and give an answer later in the talk. But I want to start here by somehow recalling somehow a particular case where this can be answered in a slightly nicer way, I would say. So the answer will be a kind of a generalization of the following result, of the following theorem. So this theorem has some restrictive assumptions. So we have to be working over a field K, which is a complete non-Archimedean field, or maybe it's even discretely valued field with residue field K of characteristic 0. So essentially, here, sorry. So yeah, said differently, I'm taking my k to be something like k parentheses maybe pi. So the field of Laurent series with a variable pi. Right, so in this case, we have the following result. So, okay, so then this category SH that I will define in a moment is equivalent to something which I denote by QUSH of KT. So something that depends only on the on the residue field. And so what is this? This is a full subcategory of SH over of GM, if you want. Okay, so it's motives over the one-dimensional torus. And it's a subcategory which is generated by some explicit objects. So let's see, this is generated by motives of maybe let me say it like this. So motive of x, where x to GM is some so it's a scheme over GM which become constant, after base change to some power map. Okay, so no, it's maybe not so well understood here, but so the idea is that there are some simple generator of this category because unipotent, and these generators are essentially motives of GM scheme that become constant, so that they are of the form GM times some smooth variety U, but this is only after making a base change by the power map for some end. Okay, I hope this is clear. So. Right. So there's an explicit way to somehow to understand the category of rigid analytic motives in terms of usual algebraic motives. So and somehow what I would like to get here is to get somehow a similar answer, but where I would which would work for any base in some sense without restriction. So where you replace k by essentially any rigid analytic space. Okay, so this is somehow what I would like to tell you about today. Yeah. All right. So yeah. So maybe I was planning to start by this is if you want the plan, and I want to start with some recollection on rigid analytic geometry. I don't know if this is necessary, but this is what I have planned to do.
Sorry, may I ask? Yes. So the theorem is that can you show a bit above?
Oh, sorry.
So that it's so this rigid SH of K is a subcategory in SH of GM. And
right,
then
yeah.
Maybe I missed it. Can you describe it inside it or?
Yeah, so it is
this equality is okay, good. That's what I was hoping.
All right, so let me try to arrange this a little bit. Thank you very much. So yeah, it is this one which is
okay, great.
Okay. Sorry. Yeah, thank you. Is this clear now?
Yes.
Thank you. Okay, so okay, so for this work somehow we were using what is called the Reynold approach to rigid analytic geometry, which is maybe not the most used one. So yeah, but I also try to make the link with somehow what seems to be more broadly used, namely the approach of Huber. Okay, so yeah, so we are using, and I'll tell you later why somehow this seems to be the more natural version for us, at least. So we are using the approach of Reynold, which is somehow nowadays you can find books where this is developed in a lot of details. And for instance, so see, for example, the book of Fujiwara. I'm not making mistakes in writing the names, and also Abyss. They systematically develop this approach to rigid geometry. So what is the idea here? Yeah, the idea is very simple. Is that so a rigid analytic space is the generic fiber of the formal scheme. So this is essentially somehow the idea behind this approach. So more precisely, one starts with more precisely. We start with the category of formal scheme. So should maybe say a bit more. So here, yeah, I think everybody knows what is a formal scheme, except that we don't we want formal scheme to have so-called a finite type ideal of definition. Okay? That's essentially the only condition that we put. So maybe this is this is a category of quasi-compact, quasi-separated formal schemes with finite type ideal. Yes. Finite type ideal of definition. So I will not say anymore this phrase here. This will always be assumed from now. Okay, so one start with this category, and then one make a definition. So one defines the notion of admissible blowup. So this is a blowup. Essentially, it's a blowup of a finite of an open finite type ideal, essentially. Okay, and then here's a definition. One define the category of rigid analytic spaces, maybe quasi-compact, quasi-separated. By definition, this is formal schemes where you invert these blowups. Okay, and so yeah, by construction there is a functor from formal scheme too, and we think about this as this functor. We think about it as maybe yeah, taking the special fiber, the generic fiber. So, and yeah, we like to call this functor like this, parenthesis rig. Okay, so this is, so you have a formal scheme, then x to the power rig. This is the associated rigid analytic space, and of course formally it's just it's said that, but we think about it in this localized category. Okay?
Sorry, why can you think about inverting admissible blobs as taking generic fiber?
Why do you think so? The question is why do I think about inverting blow up as a generic fiber?
Yeah.
That's a good question. I mean, it's not me that think like this to start with. So it's Reynold who had this idea. And I think, I mean, there is a good reason is that if you have, I mean, let's take the simplest case where you have maybe a scheme over a DVR. Okay, you have a formal scheme over a DVR, and so if you blow up, if you take an admissible blow up, this means that you are blowing up somewhere in the special fiber, and this of course does not change the generic fiber. So it's kind of clear that for whatever notion of generic fiber you take, this should be insensitive to admissible blow up. So there is at least a functor from the localized category to rigid analytic spaces, and yeah, for some good reason, one takes this as a definition. Yeah, I mean, of course, also one has to prove that this is a reasonable definition in the sense that it is compatible with the other notion, or for example, with the definition of Tate or with Huber. Right? So, and there is indeed a comparison theorem which tells you that this is indeed a good definition. Okay, I'll come to this in a moment. But, okay.
Thank you.
All right, so this is the definition, and then of course one enlarges a little bit by allowing a gluing. So sorry, SPC is essentially obtained from SPC quasi-compacted by allowing gluing along open immersions. Right, this is roughly speaking what is a rigid space in the sense of Reynold. Okay, so yeah, as I said, so one has to. I mean, this only makes sense if one can somehow compare with maybe with some more traditional definitions. Yeah, so maybe before doing that, let me make maybe a fact or construction. So if you have an object in this category, then you can associate to it. So one can associate first a topological space and a sheaf of rings and the subsheaf OX plus inside OX. In the same way that I mean, yeah, analogously to what one do, for example, for Huber spaces. So it's very easy to say what is X, what is this X under the line. So if X is given as the associated rigid spaces to a formal scheme curly X, then this X is simply the limit over all admissible blowups of X prime under bar. Okay. And similarly for OX plus, OX plus also, yeah, if you want this, yeah. Okay, so maybe, in fact, more precisely, this guy here is, I think is a limit in some category of ringed spaces, I guess. Yes. Okay. And then the OX without a plus is obtained by inverting some invertible sheaf of ideas. Okay. All right. So this is and so yeah, and with this I can maybe state now the following thing is that maybe comparison with Uber. So in case you're familiar with this, this will not really be needed later. Just for those who are, someone would like to see how this compares to Huber's rigid analytic spaces or adic spaces. Yeah, so here's maybe a fact. So there is so there is a category of adic. So we call it adic like this. This is really this is a category of there are some adjectives. Let me see if I can remember these. Uniformly. Okay, maybe something like uniform adic spaces. So you probably have, I mean, I'm sure that you have heard about the fact that if you have some, I think that they are called Tate affinoids. So these kind of pairs where you have some algebra and then the subalgebra of integral elements that you can associate to this spectrum. It was done by Huber, but then this spectrum is not always well behaved. There is this problem of not having the sheaf property always, and so on. And so this objective here, uniform, is to ensure that you don't have this problem. But yeah, anyway, so this is the category. This is Huber's, if you want, categories of adic spaces. It is you can think about it really as a full subcategory of this of these rigid spaces. So there's a full embedding of this. I can say what it does. I mean, what this embedding is doing on algebras, if you want. So if you have a Tate affinoid, if you have so it's a pair of like this, a plus minus a plus. Maybe these are not so standard notation, but you see what I mean. So this guy here is a ring, is a topological ring where the topology is defined by some open subring, which is adic and so on. And this is a subring of integral elements and some properties. Anyway, so if you have such a thing, then this spa of A as an adic space is sent to simply to you take the formal spectrum of A plus, and then you take the rigid analytic space. Okay, so this is somehow the dictionary between the two approach. So I think I don't want to say more about this unless somebody asks, but maybe move to categories of motives. Well, there's no question. So yeah, so let me now remind you what is this SH. So the construction of this category. So it's associated. So S will be now. So S is a rigid analytic space. So the construction of this category is straightforward. Adaptation of the construction of Morel-Vezzani. So yeah, so the ingredients are the same essentially. So one needs to know what is a smooth morphism between rigid analytic spaces, what is an étale morphism between rigid analytic spaces. One has to have an analog of the affine line and an analog of the Tate motives, and then somehow the construction is really the same. Let me maybe yeah, I shouldn't. Okay, so let me maybe just say very quickly. So there is a good notion of étale smooth morphisms in this category. Sorry, SPC. So it's a slightly so of course so maybe the naive guess would be to say, okay, we take an entalmorphism of a formal scheme and then look at the generic fiber. This would be an entalmorphism. This is correct, but this does not provide all the entalmorphism that one somehow would like to have. So essentially, a morphism is étal if it's only ramified. So one has to make sense of this, but if it's only ramified along the special fiber of the. So if you have a morphism of formal scheme, you call this rig étal if somehow it is only it's étal away of the generic of the special fiber, and then you use this as a. And similarly for smooth. So maybe let me say. So here the idea is that that there is a notion of rig étal morphism, which is now in formal scheme, which is more general than the notion of étal, and one uses this to define what is an entalmorphism of rigid analytic spaces. More. And this is used to define étal and smooth in this category. Okay. Yeah, I mean, this can really be done very concretely using equations. You ask for the Jacobian criterion, but only up to somehow power of uniformizer or something like that. So this can be done very easily. So there is also so here we take so the affine line is replaced. The algebraic affine line is replaced by what is called the Tate ball. So yeah, I think it's kind of clear what it is. Maybe just so to introduce notation. So we call B Bx. So if X is a rigid analytic space, this is essentially something like this. So you okay. So maybe assuming that X is curly X. So what you do, you look at formal spectrum of OX, and then you adjoin a variable to that, and then you take the rig of this. Okay, so one can make sense of a Tate ball over a base, and then yeah, there's also a version of the Tate motive, or if you want a version of GM in this case. And so then you use this ingredient in exactly the same way as one does for SH, and you get this category. So maybe more specifically, so take SH of S. What is it? So you take sheaves on maybe smooth. So you look at the category of smooth object over S. You take sheaves. Yeah, this is important. So I really we do have result for the Nisnevish topology, but somehow if I want to tell you about this answer that I promised at the beginning, I need to restrict to the étal topology. So I would, from the beginning, I would just stick to étal topology here. You take sheaves of spectra, and then you make a localization for this B1 thing, and then you invert Tate. This T-1. Okay, so this is the usual construction. Okay, right. So this is what we are interested in, and
Joseph, sorry.
Yes.
So you're not looking at the Nisnevish topology somehow.
Yeah, I mean, I said that one could look at the Nisnevish topology, and I could do this for many of the results that I will state. But if I want to tell you about what I promised at the beginning, this is the answer to this question: how you reconstruct this category out of categories of algebraic motives. Then this result only for this result, I need to be working in the étale topology. Okay,
But
but
SH,
essentially only for that result. Yeah.
But the algebraic SH is the Nisnevich SH, is the usual SH, right? In your reconstruction result.
It will be the étale SH.
Oh, the étale SH, I see.
Yeah, it will be étale SH.
Cool.
Right? So I don't know. I could start to put étale everywhere, but anyway, so maybe I should do this actually, because otherwise it's maybe confusing. Okay, for them, I mean, you know what I mean. So maybe let us erase this, and when I need to say something which only work with the topology, I will put étale. For the moment, it is generalized.
Perfect.
Okay, so this is Nisnevich. All right, so this is this is a construction, and yeah, you're right. Maybe this is better to do like this. And yeah, so here's maybe one theorem. So, so this assignment is to SH has or admit, okay, has the 6 functor formalism. So in particular, we have this somehow the easy functoriality. So given map in of regenerating spaces, we have the usual inverse image and direct image functors. So these are the easy functors that somehow they are really immediately consequence of the construction of this formula. So just, and then if f is locally of finite type, we also have the exceptional functorialities, and as usual we have that this is the same as this if f is proper, and we have that this is also the same as this one, but maybe up to a twist. So yeah, so I don't know, Tom space of omega f. There's some twist here for f smooth. Okay, and plus base change theorem, the usual formalism. So why? I mean, why did it take maybe so long to prove such a theorem? What was the difficulty really? I mean, in fact, this was known essentially under some hypothesis. It was essentially known when you assume. I mean, of course, part of it is clearly kind of obvious. So what I'm speaking about, for example, this part here. This was known essentially for f algebraizable in some sense. So so make a remark. This was known. When maybe about 10 years ago, yeah, but okay, when f is algebraizable. So if you so for example, if you have if you have a morphism of schemes, for example, which is proper over maybe some DVR, then you can associate to this. You can analytify this morphism and get a proper morphism of rigid analytic spaces. And for those kind of morphism, we had before this kind of functoriality, and we had the proper base change and so on. So, but it was unclear how one can use this somehow to prove a more general statement. Somehow the reason for this is that there is no version of the Chow lemma in rigid analytic geometry, so there is no way to to blow up your your morphism and reduce to the case where it's algebraizable or projective or something like that. So there was an essential difficulty somehow to pass to the general case, and somehow we had to really to take somehow a detour to get to this theorem. I'll try to say maybe a few words about the proof later, but yeah, this is one of the theorems that we obtain, and essentially, I mean, this was really somehow this is the reason why we started this project, is to get this kind of general theorem, and then somehow the application that, or the thing that I want to speak about now is somehow came later in this project. We're not expecting this, but somehow, yeah. All right, so this is I think is there a question?
So, sorry, yeah, could I just ask a question? Maybe I missed something earlier. So when you say the Nisnevich topology, is that going to be different from the analytic topology on rigid spaces?
I'm not hearing anything anymore.
Oh, sorry. Is
the problem?
Is it okay now?
Everything.
I'll type it. Sorry.
I think Joseph is stuck.
I think Joseph froze, yeah.
Akil, it's not you.
Oh, okay, sorry.
Shall we wait?
Joseph, can you hear us? You're muted. Wait,
yes, right. Could you unmute me? Yeah.
I think you dropped. Yeah.
What happened?
Your connection just dropped. You're back.
My
now.
connection. Okay. Okay. Sorry. How do you know that it was my connection?
Well, it works for everyone else.
It works for everyone.
Okay. Okay. Yeah. So.
You want to reconnect, and then Akil can ask his question.
Yeah, maybe I should share again the screen. Yeah.
Sorry, can I ask? Sorry, I was just wondering. So is the Nisnevich topology stronger than the analytic topology when you work with rigid spaces? Maybe I missed.
Yes, it is. Yes, it is. So, so it is not if you are dealing with over-convergent things, but I mean yeah. For example, if you take evaluation ring of height bigger than 2, it's a complete thing. Then you see it has no, it's a point for the analytic topology, but it has non-trivial Nisnevich cover because the special fiber is not Henselian, and therefore.
Right, but aren't the local rings in the analytic topology Henselian?
So it is. They are Henselian if you invert. So I mean, so okay. I tried to write this. Okay, so. If you have a point, if you have x and a point, then you can look at the local ring. This guy is Henselian, right? But then inside there is the other one, this guy here, and this is not Henselian. And because this guy is not Henselian, it has some covers. I mean, take the simplest example. Take x to be. So take V to be what is called a complete valuation ring for some pi, and yeah. So this guy, I mean, then this V is so the. This guy here is the V, and this guy here is a fraction field of this, right? And so, but this has no reason to be Henselian. I mean, if the rank is bigger than 2, If the rank is 1, it is NCDM, but otherwise. So the special fabric could be any valuation link. So you see, if you mod out by the radical of V, somehow this is a valuation link, but could be arbitrary. No condition on it. Okay. Does it answer your question? Does it sound reasonable?
Thanks.
Okay. Okay, so I was saying that this was known when F is algebraizable. Yeah, but somehow it's not clear how there is no direct way somehow to reduce it in the trial case. Okay, so maybe let me say also what is the key ingredient somehow for constructing these functors. So yeah, key ingredient for constructing the exceptional functor is the following. So we call this extended proper base change. And so it's flowing maybe proposition. So yeah, given the Cartesian square of rigid analytic spaces, with F proper and G smooth, then the exchange natural transformation, which is I guess it should be the other one. Yeah, prime G more sharp F. All right, so I didn't say it, but this guy here is the left adjoint to G upper star. And this is the usual notation that one uses, at least in motives. This is an isomorphism. Yeah, in fact, we only need this for F and open immersion, but somehow the proof is not easier in this case. Okay, so this is somehow the main result. So this is the main ingredient that we need to establish, and once we have this, it's not, then it's a kind of a formal. So there is a formal recipe for how to construct these functors using compactification and so on. Somehow, yeah, this is the. So I should also maybe comment about this a little bit. So in the case of algebraic motives, this is equivalent in some sense to the usual proper base change theorem. Indeed, if this J here is an open immersion, then you can take the complement in algebraic geometry. You can take the complement of an open immersion, and then using localization, reduce the statement to the proper base change theorem, but for the other square, for the square where you have the complement closed immersion here, and then the base change of F here. But in rigid analytic geometry, there is no good notion. I mean, there is some notion for the complement, but it's not the complement. The complement of an open immersion is not. It's not a rigid analytic space in the usual sense, and so one cannot reduce this to the usual proper base change theorem. And by the way, the proper base change theorem, the usual one, is an obvious, I mean, is an easier statement, in fact, and it even holds effectively without the maybe. So yeah, this is really somehow in rigid geometry. This is really a more somehow a stronger statement than the usual base change. And this is why we call this extended base change, because it's really it has yeah, it cannot be reduced to the other one. All right, so now let me maybe so these are somehow the one type of result that we obtain. Let me now maybe go on and tell you about the relation with algebraic motives. So in fact, yeah, so this relation somehow came up as a consequence of our proof somehow of this proposition in some sense. More precisely, somehow there's a key ingredient which is used in the proof of this proposition, which somehow also is used in the next theorem that I will state. Okay, so what is this theorem? So this is a way somehow to reconstruct the category of rigid analytic motives using algebraic motives. But before I state this, I need to introduce some objects, some notations. Okay, so let's see. Given a formal scheme, given a formal scheme, one can also define a category of motives. Maybe one could call them formal motives. Over X in the same way as before. Okay, so as before, we have the notion of an Étale morphism of formal scheme. We have a notion of a smooth morphism of formal scheme. We know what is the affine line over a formal scheme and so on. So we can do the same construction as before. And this gives us what we call FSH of X. Okay, the formal motives over X. Now, it happened that this category is not really a new one. In fact, one can show that. So the special fiber functor So, by the way, I didn't say maybe what is a special fiber functor. So if you have a formal scheme, what I call special fiber is simply the if you want the formal scheme modulo an open ideal, maybe, and then you take the reduced scheme. So it's just somehow, I don't know. It's a scheme which has the same underlying topological space and a discrete reduced sheaf of algebra. So this functor induces an equivalence between FSHX and SH of X sigma. So X sigma is a notation for a special fiber, and this is called the sigma upper star. So this is in fact it's an instance of the localization property that is well known for algebraic motives. If you have so this was proven by Morel-Wojcicki in their paper. If you have an open immersion and the closed complement, then J upper star and I upper star give you a conservative pair. It's actually the same statement here, except that the complement of X sigma happens to be the empty formal scheme, and so you get such a thing. It's really the same proof, and yeah. Anyway, so yeah, we have this equivalence, On the other hand, we also have the generic fiber functor. We have functor. Maybe let's call it eta upper star, that goes from FSH X to rig SH. Okay, so this one is taken by is obtained by associating to a formal scheme. It's generic fiber. Okay, so we have these two functors, and therefore, and they also, of course, have adjoints and so on. So there's eta or star here, and so then we also we define, or we denote by xi, maybe if you want to be, if you need to say where, for which formal scheme we would write it like this. So this would be this functor. So h x sigma going to sh, and we denote by chi its right adjoint. Okay. So we have this functor which somehow which we will use to give this this way of constructing rig SH out of SH. Right? So this is a category of algebraic motives, and we will use these functors somehow to reconstruct this category. Okay, so yeah, before I state this theorem, I have to introduce one more notation. Right, so the functor X is monoidal, and as a consequence of this, we see that so we have chi. If I apply chi X to the unit object, this will be a commutative algebra. In H sigma, and yeah, by general categorical nonsense, we get so we get I don't know if maybe a refined adjunction. Like this, so psi tilde, the formal scheme that goes from SH. Now we use this notation to now in our maybe two. Yeah, I hope this is clear. So we use this notation to indicate the category of chi1 modules in SHX sigma. Okay, so I hope this is clear. There is a functor to SH. Yeah. So, and there is also the right adjoint. So this is chi tilde X. Okay, so we have these two functors. And now I can maybe state the theorem. Yeah. Okay, so let's say maybe so that there are some technical assumptions that I will not try to state now under some mild technical. Maybe I would say some of them orally later on. So what do we have? So we have that the functor psi tilde X is fully faithful. And moreover, we have that, yeah, how do I say this? Okay, so maybe it's like this. So the natural transformation. So maybe before stating this, I should now not forget to say that now this is I don't know, or just like this in the étale topology. So here I want to look at the étale version of SH and rig SH. Okay, I will not maybe write étale, but yeah, I hope this is okay like this. So what do we have? So we have the natural transformation. So again, so it's chi tilde that goes from SH sigma so I want to think about this as a natural transformation defined on transformation okay between functors defined on formal scheme. Right, so this is if you have a formal scheme, you get a functor and one for each, and then it's coherent in the usual sense. So the natural transformation, what does it do? It exhibits the right-hand side. Right-hand side as the Rig et al. Sheafification. On the left-hand side. So this is this is the statement of the theorem. So yeah, so it's in some sense it provides provides a way of thinking about this category just so using these ones and some limits and co-limits in infinity. So maybe yeah, I should have said also this that so here we are taking sheaves, but so in the sense that so it's sheaves with values in presentable categories. Okay, so maybe it's important for the statement. So here, okay. So here pre-sheaves with values in PR. So PRL, this is the infinity category of presentable infinity categories. All right, so taking limits and co-limits in this infinity category, somehow you can reconstruct this out of these kind of things. Okay, so in this way, this is a reconstruction or a construction, I don't know, theorem that allows you to think about rigid analytic motives using maybe purely algebraic motives. So this is a statement. In fact, the statement. Maybe yeah, I should maybe say what is Rig et al. I don't know if you want, but okay, I'll do it. Oh, my time is more or less over. I don't know how much time I can take.
How much time would you like?
I don't know, maybe 5 minutes or something like that.
Sure.
Yeah. Yeah. So I still have one theorem that I would like to state. Actually, this is maybe it's. But anyway, let me say this remark. Maybe what do I mean by Rig et al. Topology? So Rig et al. Is a topology on formal scheme given as follow. So a cover, or sorry, a family the cover simply if when you look at the associated when you look at the generic fibers, so you put rig everywhere. This is a cover, is an Untitled cover. And so said differently, this is the topology that makes the site of formal scheme equivalent to the site of rigid analytic spaces for the Untitled topology. So it's and so I mean, yeah, it's a fact that this category rig SH is a sheaf for the Untitled topology, right? It's kind of expected, and this is so this guy is a sheaf, and when you sheafify this guy, you get the same thing.
Joseph, wait,
yes.
can I ask you a quick question? So the SH with modules of chi is taken with respect to the algebraic Untitled topology. Is that correct? Like it's not in this.
Yeah. I mean, here there's only a Untitled topology. There is only algebraic Untitled topology.
Yes.
There's,
and then the point is that it sheafifies with respect to this topology that has like some analytic flavor.
Yeah.
Thank you.
Yeah. All right. So I mean, so in this statement there is one thing which is somehow inexplicit, which is in fact this chi1. And so in fact, so for this statement to be really meaningful, I should tell you what is this chi1. And in fact, that we also have a result which describes this chi1 also purely algebraically. Right. So up to now in this formula, there are two somehow non-algebraic things. One is this chi1, and then the second is this rigid topology. I mean, of course, one could argue what is algebraic and what is not algebraic, but I think you see what I mean. And I think there is no way to get rid of this topology here, but there is a way to give also a purely algebraic description of this guy. And this is the next theorem. In fact, this is maybe even more. Yeah, it's actually maybe the most difficult part. In fact, this is the description of this chi1. So here's this theorem. So let's see. What should I say? Okay, so we can compute chi1 algebraically as follows. So I assume that you have a scheme B, so B a scheme, or sorry, B, let's say maybe quasi-compact scheme, B sigma closed subscheme, of finite presentation, and B eta, be the complement. Okay, so then you have the usual. So it's called J, the inclusion of B eta, and I, the inclusion of B sigma. Okay, so yeah, so then you could also look at the formal completion of B at B sigma. Okay, then we have the chi, so we have this chi B hat 1. So what is it? It's an algebra in SH, B sigma. Right. So the point is that the special fiber of the formal completion of B is just B sigma. Yeah. So right. So okay. So we can think about chi B hat as an object here, and in fact, so this is given by the usual operation I upper star J lower star of 1. Okay, and so these are so here are the I upper star. This is the functor from SH B to SH sigma, and J lower star. This is SH P eta to SH P. These are the algebraic functors. Okay, so again, this is giving us an algebraic formula for this chi B1, and one should say that this object here is very much computable. So there are techniques to compute this. For example, if you know that that B is a regular scheme and that your B sigma is some kind of normal crossing divisor, there's a very explicit formula for this object. Right. So in this sense, it's somehow it's giving you a better maybe. I mean, the combination of these two theorems is really maybe what I would call the algebraic description. And maybe just a final remark. So this really general. So combining these two theorems. Combining. We can recover this old theorem of mine that I said at the beginning. I said the old theorem I stated at the beginning, but only in data topology. Yeah. In data topology. It's still unclear how one could formulate even a more general, so a generalization of this old theorem, even for QP. I think it's unclear for me unless you are in data topology. So if you are not in data topology, I don't know how you could write down SH of QP in terms of, I don't know, SH of FP, sorry, rig SH of QP in terms of SH of FP or some simple schemes over FP. Okay, all right. So I guess I can stop here. Yeah.
Let's give Joseph a round of applause. Is there any question for Joseph?
Yeah, I have a question. So in this equivalence between formal SH and algebraic SH, are you using also just étale topology, or it's an equivalence for Nisnevich topology?
Yeah, for that it works for in the Nisnevich and the étale topology.
Okay.
So it's true for both topologies. But I mean, this is really the étale topology on formal scheme. So it's not rig étale, because I mean it doesn't even make sense to speak about rig étale there, because in the construction of FSH we only consider smooth formal schemes, and typically this rig étale topology is only defined on non-smooth formal scheme over a base, because you have to blow up and destroy smoothness.
Okay. Thanks.
I have a question. Is there a CDH style descent result for this rigid SH given your 6-functor formalism?
Yeah, it's a good question. So let's see. I mean, I don't. Yeah, is there? I think, I mean, for CDH you probably can do something, because it's generated by square. So it's, I mean, and you have these. There are some simple criteria for to decide when something is a CDH descent. I mean, I'm just a bit worried. I'm trying to understand what is CDH for generating spaces. I'm not sure.
Right, that's part of the question, I guess.
Yeah, it's part of the question. Yeah, I was discussing this recently with Alberto, but I don't remember what was. I mean, yeah, of course, one could, of course, take the naive thing and you add blowups, and you have étale covers, and you add this blowup square, and then I think the answer is kind of yes, there is CDH descent, just because you have this nice criteria for CDH descent. We were trying to see if there would be some kind of V descent for this topology introduced by Scholze, where somehow essentially everything is a cover. And yeah, we were somehow, it was not clear if this was, there was some technical issue to prove such a thing, so we are not sure what to think about this for the moment.
have a question too. Can you hear me?
Yeah, but I don't know who's speaking. I can't,
Yeah,
I
it's,
can't see you.
hang on.
Okay.
You see me now?
Yes.
Do you have any interesting example of an analytic motivic spectrum?
Yeah, I don't know what is an interesting example, but I mean, like, do you know one interesting example for usual for SH, for the usual SH, like
Yeah.
MGL, for example, or what would you consider an interesting spectrum?
Especially interesting would be one which is not an analytic analog of the
Oh yeah,
motives, of course.
then I don't know. Yeah, then I don't know. I mean, I was so. I mean, of course, whenever you have something interesting in the algebraic setting, you can just take the analytification of it and you get something, something which is really, I don't know. I mean, of course, you could. I mean, you know, like for example, you can take étale cohomology of rigid spaces, and you can represent it there. This is not an analytification of something coming from. Yeah, I don't know. I mean, yeah. Yeah, I can't think about something else, but I mean, essentially, whatever you can do for algebraic SH, you can also do here. And but I mean, I think that somehow, if you want motivation for that, I mean, my motivation. So when I started to think about this was really, I mean, in fact, was really this main theorem that I stated at the beginning. Because somehow, yeah. So let me go back to the statement. Oh, right. So this statement here. So the reason I was somehow doing this kind of things is because what one can do, one can look at SH of K, and then you have a functor like from here to here, which is like analytification, and then you can compose with this equivalence, and then you get a functor like this. And this is this somehow is like a well-known. I mean, it's a well-known thing. It's called the limiting construction. So, for example, in Hodge series, you have this limiting Hodge structure. Whenever you have a variation of Hodge structure over a puncture disk, you can somehow take its limit to 0, and this is somehow the motivic analog of this construction. And somehow, yeah, doing the more general thing is also some kind of this is called the formalism of Banshik cycle, and somehow it's doing something like this. So if you have a variety, I mean, like the B I was considering at the end, if you have an algebraic motive over B, then you can somehow take its analytification, and this looks like somehow taking the limit over to some special fiber. So. I mean, yeah, I don't know if there are. I mean, there are probably also some good reason to consider rigid analytic motives, but I'm just telling you how somehow I got interested in these kind of things.
Thanks.
Okay, if there's no other questions, let's give Joseph another round of applause.